much involved in the discovery of the Higgs boson that you heard about in the last couple of years. The research labs that did the work are right over on the first floor, and what Penn is responsible for in that project is building the detectors. When you're detecting elementary particles, they are moving really fast. And it turns out that along with when you got the signal, the movements are so fast that the next question is, how long did it take the signal to go from the detector to the box that I recorded it on? In other words, how long does it take electricity to move in a wire? This is a really interesting question. I mean, for most of us, you know, like you walk in a room and throw the switch, and it's not like, okay, I got to wait for the electricity to get to the light, you know, and I'm going to trip and break my ankle. No, as far as we're concerned, electricity takes no time to move. But if you're trying to detect a Higgs boson going at nearly the speed of light, you really care, well, how long did it take that signal to get back to my detector? So this is a gadget that lets you calibrate your wires. This thing creates a pulse that's only about 5 nanoseconds big. What's a nanosecond? What does the prefix nano mean? -9, cool. Or what fraction? 1 billionth. So this creates an electric pulse that's a billionth of a second long. And we're looking at that here. And that is the benefit. So you just go out and buy these computers that are like a 1 gigahertz computer. And you think, well, I got more gigahertz than you do. And the guy says, well, no, you don't, because I have a 2 gigahertz. What the hell's a gigahertz? A gigahertz is a billion operations a second, which means each one takes a billionth of a second. So your computer is the best timing device that's ever been known in history. You can time things to billionths of a second. And so this is a device that, notice, M is 20 nanoseconds. So each box represents 20 nanoseconds. What is a nanosecond in terms of behavior? Light can travel a foot in a billionth of a second. Okay? Important sense to have. So why don't we notice? Because a second is not a accidentally chosen interval. A second is about the shortest time that people can notice and react. Okay? That's why didn't we go down to smaller intervals? Because mostly people can't react any quicker than that. Okay? Reflex times are typically a second. A lot of that has to do with how long it takes the signals to go from eye to muscle. It's the reason you can't catch a fly, because the fly's eye and the fly's wing are a lot closer together than your eye and your hand. So the fly sees your hand and he can react quicker than your eye that sees the fly. Okay? Unless, of course, you're the Karate Kid and you can grab them with chopsticks. Okay? But needless to say, okay, our timing can now get much quicker because our computers are quicker. So here is a pulse that takes something between 5 and 10 billionths of a second. We're running it into this wire. How long is this wire? Well, luckily, Brandon is going to illustrate for me. Okay, and take this. Okay. So we're going to run this. Whoa. How did it get 10? What evil's working? What's it made? Okay, you know what? We got. You take the end, I'll take this. Okay? All right. Okay, so Brandon's going to roll this out. This is a very long wire. We are sending this signal into this wire. Okay? And you're at the end. And we come down to here. And so he is 33 feet away. and the wire goes out and back, so he's 66 feet away. So if electricity moves at the speed of light, we expect it's going to take 66 billionths of a second, okay, for this pulse to go through the wire and come back. So we're going to take the end of this wire and we're going to hook it up to the channel, the blue channel there. And it's going to show us when the pulse gets back, okay? And so we plug this guy in, and there's the returning pulse, okay? And so what do we got? If we take this tip here, all right, and we should be able, let's move this tip over to where it's right at the beginning of that box, and we are 1, 2, 3, 4, 5 boxes. Each box is 20 nanoseconds, so it's 100 nanoseconds to make this trip. Now we said if it's 66 feet, light could do it in 66 nanoseconds. So it turns out light can do it in 2/3 of the time. Okay? That this electricity, if we invert 2/3, this is 3/2. So the electricity takes 1.5 times the rate of light. But that's pretty amazing. The electricity is traveling nearly the speed of light, and we are measuring it. This is not an accident. We actually got this cable from the high energy guys, and this cable is not labeled by length, it's labeled by time. This is a 100 nanosecond cable. And they would hook this up to the sensor and to the receiver, and they would know that we've got to build in 100 nanoseconds of time because that's how long, you know, so if we get a signal at this time here, we know what happened at that time out there. Okay? Which is a very important thing when they're making these records. And so this kind of thing lets you do all sorts of stuff that you didn't used to be able to do. One other very interesting thing that happens, I don't know whether you may have noticed, it turns out that electric pulses in wires actually reflect off the end of the wire. So we just shrank the time down. Now the boxes are 40 nanoseconds. And you notice the signal goes out the wire, bounces off the end, and comes back in the same wire. And of course, it returns and gets recorded here in half that time. This is one of the reasons you've got to put end loads on cable TV wires, because the signal in your cable TV wire will actually come bouncing back and give you a ghost image. Okay, and we can see all of that here if we slow it down. If we speed it up, we can ignore the reflection and just look at the original signal going out through the yellow end of the wire and then coming back through the blue end. Okay, we are going to break.